Now we'll talk about decidability of halting problem. You know what is halting problem, right? Halting problem is a collection of strings. That means it's a language where that collection of strings are having a format called m hash x, where m is treated as a Turing machine code, x is treated as some input, and if m halts on x, really m is a Turing machine and x is some input. If we run that Turing machine on x, really m halts, then we collect such strings. Okay, so it forms a language. Now the question is there any total Turing machine for it? But we know that there is a ordinary Turing machine. How to design it? Let me go very fast because already I taught you. Take m, take x and simulate m on x using your code. Let's say new machine, this one, let's call it as n. Then this machine n is simulating m on x. When simulating m on x, if m Turing machine goes to final state, otherwise reject state, that means we say that m halts on x. We can find out, right? Whenever m really halts on x, that simulated to be simulated Turing machine will go to final state or reject state. Then I will go to accept state. I'm talking about this accept belongs to n. If m really loops on x, then we also loop. Correct. In that way, so we can design a Turing machine. This is a Turing machine. Whenever this underlying the input will be m hash x, and really that m halts on x, then it is accepting. Otherwise, it is looping or anything. Correct. So that means this is a Turing machine. But I want total Turing machine. Why, sir? Then only that problem is called decidable problem. At this moment, this is semi-decidable problem, halting problem. Okay, so can we say that this is also a decidable problem? No, because there is a proof that there is no total Turing machine. Some students argue like this, sir, we don't require proof. Why? My common sense, otherwise my strong feeling is there is no total Turing machine. Then I ask that student, how can you say that? Sir, I tried some possibilities. Okay, if you tried some of the possibilities, it doesn't mean that there is no such Turing machine's existence. Correct? Maybe you did not try all possibilities. How can you say that there is no total Turing machine? Maybe your friend already achieved it. Correct? That is one thing. Second one, in the future, after 10 years, someone might construct a total Turing machine for this problem. That's why you have to give a proof that there is no Turing machine, total Turing machine. Then only the problem will become undecidable. Understand? So here I am going to, if you give total Turing machine, then this problem will become decidable. If you prove that there is no total Turing machine, then this problem will become undecidable. But what if you don't know whether there is a total Turing machine or not? What can I say? Example, let me ask one question. 2 into 2 equal to something 5. I am asking true or false. So whether this statement is true or false depends on knowing whether 2 into 2 equal to 5 or not. Correct? Example, case number 1. Sir, I know that 2 into 2 equal to 4. Yes, if you know that, then this statement will become false. Correct? You can decide that it is false. Now if 2 into 2 equal to 5, let's say if really 2 into 2 equal to 5, then you can decide that it is true. But let's say there is a situation like Raju. So Raju doesn't know anything about multiplication. He doesn't know how to do multiplication. He doesn't know what is number, everything. Then when you ask 2 into 2 equal to 5, then he will put a question mark. So he'll say, what is this? I don't know anything. When you don't know anything, then we can't do anything. That means it is your inability. Correct? That means you have a problem in understanding the things. Similarly, when given a problem, let's say kind of halting problem, then if you design total Turing machine, then we say that that problem is decidable. If you cannot design total Turing machine, and if you have a proof for that, that means no one can design, then we say that problem is undecidable. The third case, let's say you don't know anything whether we can design or not, like 2 into 2 equal to 5 and Raju's situation. So if you don't know anything, that is your inability. Okay, try to understand the differences between these three. Okay, when you don't know anything, then that is your inability to solve the problem. Then don't decide that something undecidable or decidable. Okay, you are not able to solve the problem. Yes, there are a lot of problems in the world, sometimes we cannot solve. Then at that time we should keep quiet, but we should not decide that this cannot be solvable, this can be solvable in that way, unless you have a proof. Here now People, now I will tell you the story of this halting problem. People tried solving this problem. That means people tried creating total Turing machine for this problem, but everyone failed. So here now I am going to give you proof that no one can really get a total Turing machine. Okay, so that proof we will see. First of all, this proofs model is proof by contradiction. We assume that, let's say, there is a total Turing machine. Statement number 1, let's assume that there is a total Turing machine for halting problem. Really, if there is a total Turing machine, then halting problem will become decidable. But I am going to prove that it is undecidable. Okay, I am going to prove that there is no total Turing machine. But sir, why you write this one assumption? Okay, so we start with this assumption, and after that we contradict this assumption. That means we prove that it is wrong. Second statement, really total Turing machine exists. What is the functionality of the total Turing machine? The total Turing machine should have this kind of structure, right? Let's say this is your total Turing machine for halting problem. Now if you give input suitably, that means what is the input we have to give to this total Turing machine? Instances of that halting problem, correct? That means you will be giving some input like this, m hash x model. Really, m hash x is such a way that m halts on x, your total Turing machine should do what? Really, it is a total Turing machine for halting problem. M hash x is a string in your language, correct? We should say accept. I use yes also sometimes interchangeably. Yes means it is accepting. Total Turing machine is saying that yes, m halts on x. Now, if m does not halt on x, let's say it is saying no. Okay. Now, sir, if m is not at all a Turing machine code, that means it's not a valid code. Still, if it is not valid code, otherwise m does not halt on x, in all the cases it is going to say no. Then only it will be total Turing machine. Remember, total Turing machine should always decide yes or no. That means what is our question? Whether m halts on x. M halts on x, that is our string. Then it is our string. That means if it is halting problem string, it should say yes. If it is not halting problem string, it should say yes, no. Okay. Now, example, let's say you have a Turing machine m1. Okay. Now there is an input called 001. Here m1 means it's a binary pattern, right? So m1 hash 001. Really there is a total Turing machine. If you give this input here, m1 hash 001, then this halting Turing machine is going to say that yes. That means this total Turing machine is going to say yes. And if really m1 rejects, example, really the situation is like this. m1 is a Turing machine. If I feed 001 to that, m1 rejects 001. Sir, how do you know that? Let's say God helped me in understanding that. Let's say God said that m1 actually rejects 001. Really that is the case, then what this total Turing machine should say? When you feed m1 hash 001, since rejection is also halting, that's why it should say yes. Sir, when this total Turing machine will say no? If m1 loops on, this Turing machine m1 loops on 001. If there is an infinite loop, then it should say no. Otherwise, m1 is not at all a Turing machine code. Then still it should say no. That is what, the functionality of your total Turing machine. Yes. Finally, you understand that there is a total Turing machine, right? Just assumption. I have not proved it. I have not constructed it. But really there is a total Turing machine. It should look like this. Now I am going to construct a matrix. Using that matrix, I am going to prove that this kind of machine does not exist. Okay. We will see that. First of all, let me depend on this total Turing machine. My dear total Turing machine, what is your functionality? Given a Turing machine code and input x, you are deciding whether m halts on x, right? You remember it. Now, if really such machine exists, I can fill this table. How you see? What is this table, sir? Slowly you will understand. I write all possible Turing machines here, all possible inputs here, and I ask this total Turing machine about the details. How you see? Example, epsilon is one string, correct? So after that 0, then 1. I list out all possible strings. Please help me. Epsilon 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, so on. Okay. Now here I take all possible Turing machines. So what is Turing machine? This is Turing machine. So m means what? A binary encoding, right? So since I don't know whether, because we are going to give an input anything, right? That means maybe valid Turing machine, may not be. That's why what I do is I take all possibilities. That means I assume that, let's say, epsilon is a Turing machine. May not be, right? So they see only Few binary patterns are going to be valid encodings, others are invalid. Don't worry, still take all possible binary patterns and say that it is a Turing machine. Example, epsilon. M epsilon is a Turing machine whose binary encoding is simply nothing. Okay, empty string. Sir, such Turing machine does not exist, right? At least one action should be there. At least number of states. The description should be there. No, what is how many number of states and how many? What is the final state? Everything. Where is the description? Yes, that's why it is an invalid Turing machine. I know that, but don't worry. This is an intelligent machine. Correct? This total Turing machine should accept any pattern, right? I can give any pattern. Like I give like this also. Epsilon hash epsilon, because really it is a decidable problem, really there is a total Turing machine. If you give epsilon hash epsilon, what the total Turing machine should do? Okay, what is your opinion? Forget about this total Turing machine. What is your opinion? This epsilon Turing machine accepts epsilon, halts on epsilon. Sir, epsilon is not at all a Turing machine, sir. Then it should say that means what? So this is not that means it's not halting, correct? So you can treat like this. Really the question is like this: epsilon is halting that Turing machine. Is it halting on epsilon? No. Then this total Turing machine should say no. Finally, you remember, whenever we give invalid description, it should say no. Such a machine should exist, correct? Now, because for everything it should answer yes or no, then only it is total Turing machine. When it should say yes? Whenever it's a valid encoding and it's a valid input, then there is a hash in between that, then it should say really that valid Turing machine encoding halts on that input, then it should say yes, right? So we'll see now. So Mr. M epsilon, do you halt on epsilon? We simply construct like here. We give here M epsilon hash epsilon. This is going to answer it. Take the answer. Let's say it said no. I write no. No means 0. Okay. Yes means 1. Remember it. For no I am writing 0. For yes I am writing 1. That no and yes will be given by this total Turing machine. Sir, what if this total Turing machine won't answer? Can you construct this table? No. But why the total Turing machine will answer? Definitely has to answer, because that is the definition of total Turing machine. For every input it should answer something. Now I'll give M epsilon hash 0. Since M epsilon is not at all a valid Turing machine code, so always the total Turing machine will say no, it won't halt in that way, correct? So this will be the pattern. Now let me write M1. Now my interesting question here is, M1 is a Turing machine. Okay, let's take M0 first. M0 is a total Turing machine whose binary encoding is simply 0. Okay, now, and my question is M0 hash epsilon. This is my question. A Turing machine whose code is 0, will it halt on epsilon? Assume that, let's say, M0 is a valid Turing machine. That means this 0, having only one 0 in the encoding, is a valid Turing machine. Don't ask me why it is valid. Maybe valid, maybe invalid. But assume that, let's say, it is valid. Okay, for time being, so that discussion will be easy for us. Otherwise, we can take one valid encoding, not a problem. That's why I assume that M0 is a valid Turing machine code. Now I'll ask, my dear Turing machine, you know everything. You are a total Turing machine. You know everything about all the Turing machines. You tell me about my beautiful Turing machine M0. M0 halts on epsilon? Is a question. Then after some time, it will definitely say yes or no. If it says yes, that means it is saying that it halts. Okay, then I write 1. Otherwise I write 0. In that way I fill the entries. Now you slowly understand that really there is a total Turing machine, then it knows about every Turing machine and every input, right? That means whether a Turing machine halts on the particular input, this Turing machine knows. Based on that I fill these entries. Okay, now these are the table entries. M00 is a Turing machine encoding. If that halts on epsilon, write 1. Otherwise 0. Now no doubt, right? Definitely such matrix should exist. Now see the situation. Let me fill blindly. M0, M00, so here it is M11 actually. M1, then M00, M01, and systematically I am writing, that's it. M10, M11. Let me fill entries randomly. Okay, 110010. Okay, I am assuming that these values are given by this total Turing machine. 0 0 1 0 1 0 0 1 1 0 1 1 1 0 1 1 1 0. Okay, now again I use Mr. Cantor's argument. Did you remember the Cantor's argument? Take the diagonal. Okay, so you don't understand anything, I know, but after some time you'll understand everything. Okay, if you don't understand anything after completion of the course video, again watch it, you will understand it, because it's a little bit tough topic. Okay, now my question is, this is a diagonal, let me take that diagonal. Okay, so what is the diagonal? 0 0 1 0 0 0. In that way it's an infinite length string. Now let me do, this is diagonal, so let me do d dash. If I do d dash, it will become 1 1 0 1 1 1, so on. Now question here, what is the relation between d and d dash? If d is any bit is 0, the corresponding bit of d dash is 1. In that way, quite opposite, correct? Now sir, why are you doing this thing? I will tell you. Now I target this total Turing machine. Mr. Total Turing machine, do you really exist? It says yes, I exist. That's why I gave you all these entries. That means you answer any Turing machine. That means you answer any question about Turing machine. Yes, if you ask this kind of question, give me a total Turing give me any Turing machine M and give some input X and put a symbol like this hash between them, so that I can understand that this is Turing machine code, this is input. If you give this kind of input, then definitely I say whether this Turing machine code halts on X or not. Okay, such a capacity I have. That is what the argument of total Turing machine. Then I ask, you are wrong, Mr. Total Turing machine, you can't answer for everyone. Why? I am going to construct one total Turing one Turing machine, because you are answering about everyone, right? Then you should answer about my Turing machine also, correct? Then this total Turing machine says, yes, I answer about everyone. You give me Turing machine and input. If I don't answer, then I am a liar. I don't exist. If I answer, then I exist. You should agree that. Yes, we agree that. Okay. Now we'll construct the difficult Turing machine for which this total Turing machine doesn't have answer like yes or no. I'm going to construct the Turing machine. Okay. So let's say this is your Turing machine, which is Kiran's Turing machine. See now, total Turing machine is not going to answer about Kiran's Turing machine. Such a way I am going to design. Step number 1. What is the functionality of this Kiran's Turing machine? Is it takes input X, anything. Okay. Now on it assume that it has multiple tracks. In one of the tracks it is going to write X followed by X followed by hash. Yes, it is possible, right? Your Turing machine can be designed such a way that it takes input and it will copy somewhere, it will copy another time and it will put hash in between. That's not a big deal, right? Then your Kiran's Turing machine is going to take code from this total Turing machine. Yes, it is possible. We know that because this total Turing machine says that I exist. Really it exists, it will have a code, right? Then I am going to, your Kiran's Turing machine is going to simulate, it is going to take code of, let's say this is total Turing machine, right? Code of this total Turing machine into another track. Yes, it can copy it, not a problem. Remember one thing. So every Turing machine will have a code. If there is really a total Turing machine, its code can be, we can use it in another Turing machine, not a problem. Already we have seen that kind of cases. Now, what Kiran's Turing machine is going to do is, this code of this total Turing machine, it is going to run on X hash X. Sir, we can't take code of total Turing machine is one argument students will have. That means what? Why we can't take? There is no such code. If there is no such code, this total Turing machine should agree that it doesn't exist. But there is a total Turing machine. If really this total Turing machine exists, then we can take the code and we can simulate that. That's why, see, how did you fill these entries? By executing this total Turing machine, right? Similarly here also in Kiran's total Turing machine, Kiran's Turing machine, I am taking code of total Turing machine and I am simulating this X hash X on this total Turing machine. That means I say that Mr. Total Turing machine, you please run on X hash X. Whatever the answer you give, please tell me. So example, let's say this total Turing machine says that on this input X hash X, recall everyone, total Turing machine takes input M hash X and M halts on X, any Turing machine code halts on X, it says yes. otherwise it says no, right? You know the functionality of total Turing machine. Now this X halts on this X, then it is going to say yes. This X doesn't halt on X, then it is going to say no. Correct? Now, sir, what Kiran's Turing machine will do? Kiran's Turing machine is going to revert the things. That means if this total Turing machine says yes, then Kiran's Turing machine says no. This total Turing machine says no, then Kiran's Turing machine says yes. Simple. That means we are running x hash x on total Turing machine. Whatever the result you get, we are complementing. That means directly we are saying no here, yes here. Okay, forget about that. If you do that, what happens, we'll see. Whether you understand it or not, if you want to realize, let's take a random input epsilon. What Kiran's Turing machine is doing, we will see. Whenever you give epsilon to Kiran's Turing machine, so first your Kiran's Turing machine will write epsilon hash epsilon. Okay, fine. Then it will run this total Turing machine on epsilon hash epsilon. If you run this total Turing machine on epsilon hash epsilon, what happens? It will say yes or no. When it will say really epsilon halts on epsilon. Epsilon halts on epsilon, no, right? So it won't halt. Then what are we doing? Really epsilon doesn't halt on epsilon, then this says no. If it says no, then Kiran says yes. That means Kiran's Turing machine says yes. Such a machine is Kiran. Now, exactly, I am writing, Kiran's entries now. Okay. So finally, Kiran is a Turing machine, and Kiran's Turing machine on epsilon is doing what? Finally, end of the day, it is saying yes. That means 1. Okay. Now one more time. Don't worry, you understand slowly. If I give input 0, 0 to Kiran's Turing machine, what Kiran is doing? One more time we'll see. Simple. Kiran copies that 0, 0 into track number 1. He will make 0, 0 hash 0, 0 first. It is possible. After that, Kiran copied the so-called total Turing machine's code, and he simulates the total Turing machine's code on 0, 0 hash 0, 0. Really 0, 0 halts on, because we know the functionality of this total Turing machine. This is nothing but this is. So 0, 0 hash 0, 0, if you give to this total Turing machine, what this will do? If 0, 0 halts on 0, 0, it says yes. If 0, 0 not halts on 0, 0, it says no. We have already table. Consult the table. What this total Turing machine already told? 0, 0 on 0, 0. This diagonal entry says that. So we got like this. 0, 0 Turing machine on input 0, 0. We have 0 means it does not halt. Then this Turing machine is going to tell that. Sir, why this will tell like that? It tells like that only because based on that only we wrote it, correct? That means definitely this total Turing machine, if you simulate on 0, 0 hash 0, 0, it is going to say no. When it says no, Kiran's Turing machine is going to say yes. That means on 0, 0 we have 1. So that is nothing but this diagonalization D dash. D dash is nothing but simply this Kiran's Turing machine's results on every input. So here example we see this case 1. In this place we have 1. Okay. So what I am going to do is, of course, what is that input? 1 and 1, right? Now if you give 1 as input here, what Kiran's Turing machine is going to do? First it will copy 1 hash 1. Now 1 hash 1 will be simulated using total Turing machine. Then 1 hash 1's result will be directly this one, correct? Then 1. 1 hash 1's result is 1 by this total Turing machine. This total Turing machine says that yes, 1 halts on 1. It says yes. But it says yes, Kiran's Turing machine won't believe of that. It will say no. Such a way I designed it. So now finally no. No means 0. That means on input 1, Kiran's Turing machine on input 1, what is the result? No, 0. So in that way finally Kiran's Turing machine's results on each and every input is nothing but this one. Okay, finally I can say like this is Kiran's Turing machine's result on each and every input. Remember it. Okay, that's it. Now if you don't remember the construction also, don't worry. There is a Turing machine called Kiran's Turing machine. On each and every input, whether it says yes or no, that means whether that Turing machine halts or not is this one. Kiran Turing machine on 0 halts. Kiran Turing machine on second input. Sorry, Kiran Turing machine on epsilon halts. Kiran Turing machine on 0 halts. Kiran Turing machine on third string 1 doesn't halt. Kiran's Turing machine on 00 halts in that way. So this is the summary. This is the behavior of Kiran's Turing machine, and because of this construction it happens. That is what diagonalization. Okay. Now we are going to prove that this total Turing machine is invalid. How, sir? I asked this total Turing machine. Really, my dear total Turing machine, you exist, then you can tell about halting problem. I mean, whether a Turing machine halts or not on a particular input for every Turing machine, correct? Then only it is a total Turing machine. That is what the functionality of total Turing machine. Then I asked directly total Turing machine. My dear total Turing machine, do you answer about every Turing machine? Yes. Do you answer about epsilon? Yes. Please answer. Epsilon halts on epsilon or not? See, I already answered. You see, epsilon halts on epsilon. 0 means no. Oh, then 101 is a Turing machine code and 101 is 100 is the input. 101 halts on 100. Will you tell? Yes, definitely I have to tell. Then only I am a total Turing machine. Then definitely there will be an entry called M101 Turing machine. The Turing machine name is M101 and input 100 here somewhere. Definitely there is an entry. Please check it out. So now you understand clearly that how we created this matrix. This matrix is all about, you know, the decisions of this total Turing machine and on each and every input and each and every Turing machine. Now I am going to claim one thing here. Kiran's Turing machine does not exist here, first of all. Then assume that, let's say, it does not exist. I prove that. Then why it does not exist here? Why Kiran's Turing machine cannot exist here? We'll see that later. But really there is a total Turing machine. It can answer about everyone, right? It should answer about Kiran's Turing machine also. Then I ask like this. My dear total Turing machine, what about you? What is your opinion about Kiran's Turing machine? Kiran's Turing machine on epsilon, will it halt? Then total Turing machine says, yes, I answer. I say yes, otherwise no. See the table and check it out. I'm a little bit busy now. Go and check. I already answered about Kiran also. That is a very interesting point. If this total Turing machine cannot answer about Kiran's Turing machine for any input, this is not a total Turing machine. Will you agree? Yes, you should agree. Now, but Kiran's Turing machine not possible. I mean, Kiran's Turing machine is not a entry, not a row in this matrix. Why, sir? So Kiran's Turing machine's first position, you see. Really, Kiran's Turing machine entries are there here. There should be one row like that, correct? So what is the Kiran's Turing machine's row? This one, 1 1 0 1, the 1 1 so on. It is nothing but diagonals complementation, right? Then the first bit, if you see in the Kiran's Turing machine, it says that Kiran says that on epsilon I halt, but that Kiran's Turing machine cannot be this one because this Turing machine on epsilon is not halting. Correct. Now this row is not second row. Why? In the second row, if you see the second position, it is 0, but here definitely it will be opposite. Such a way we designed. Now this row cannot be third row because in the third row, third position is 1, our position will be 0. Such a way we designed. Don't, you know, it's not a surprise for us. Sir, what if it is 1000th? Kiran's Turing machine's row is 1000th row? How can you justify, I mean, how can you defend yourself? Really, Kiran's Turing machine's row is 1000. On 1000th row, go to 1000th bit. Whatever is let's say it is x, let's say it is 0. Because we did complementation, then in Kiran's Turing machine, 1000th bit will be exactly opposite to 1000th row's 1000 bit. So that cannot be 1000th row. Now in that way, whatever the row number you tell, then I deny that that is not my row. That is not Kiran's Turing machine row. Okay, so one more time I'm telling. Let's say you want to claim that this is Kiran's Turing machine. What is the row number? 1, 2, 3, 4, 5, 6. You want to say that 6th row is Kiran's Turing machine's information. He is very genuine. This total Turing machine exists and he already answered about Kiran Turing machine also about haltingness. Then you created 6th row. Then I directly ask every student who is watching this lecture, go to 6th position in this 6th row. That is part of diagonal. Whatever the bit you have, that is 0, then we did complementation. Then we got opposite behavior. We have a opposite behavior. That means this is not Kiran's Turing machine behavior. Correct? Such a way we planned it. Because 6th Turing machine on 6th input halts, then we did not halt. If it does not halt, then we halt. Such a way we designed it. So Kiran's Turing machine cannot exist here. That means Kiran's Turing machine doesn't have any row. But this fellow said that I can answer about anyone. Really, he can answer about everyone. Then there should be a row for Kiran also. There should be information about Kiran. That means Kiran's information is missing. Then this total Turing machine was not able to answer at least one Turing machine's information. That's why halting problem is undecidable. Initially, we thought there is a total Turing machine and we constructed it. I mean, we did not construct, we assumed it. After that, end of the day, whatever the way you assume total Turing machine, finally it cannot exist because always we get a contradiction, right? So now some of the students will have doubt. Sir, in the future, let's say if God creates a total Turing machine for halting problem, okay, let's say God creates a total Turing machine. Then that is a starting point for me. Then again I create a Kiran's Turing machine. If God creates a total Turing machine for halting problem, we can create this kind of entries, correct? Then God can answer about every Turing machine. Then I construct diagonalization, you know that method, right? So I am going to construct Kiran's Turing machine. Please go through Kiran's Turing machine's behavior. So Kiran's Turing machine's behavior is little bit weird, so that this total Turing machine cannot guess or cannot answer. Because really Kiran's Turing machine, I mean, if this God's total Turing machine can answer about Kiran's Turing machine, there should be a row here. But such row cannot exist because same argument, right? What we did so far. That's why finally halting problem cannot have total Turing machine. Blindly remember it. So halting problem is undecidable because there is no total Turing machine, right? So not only me, right? No one can create it because we gave a mathematical proof for that, right? So remember this important point. Halting problem. What is halting problem? Halting problem is nothing but collection of strings in the form of m hash x such a way that m halts on x. Such strings, if you collect, it forms a problem or property or a language. Such language is called undecidable language because that language doesn't have any total Turing machine. But this language has Turing machine. We can construct a Turing machine for it. In one line I will tell you. Simple. Take a design. Take m and x. We know the Turing machine code, right? Simulate this m on x. If it halts, say yes. If it doesn't halt, then you also be in loop. Then that will be a Turing machine. But you are not saying no answer, right? We are saying yes, really m halts on x. That already I covered in the some of the lectures. Go through it. So this is about m halts on x problem. So m halts on x problem has a Turing machine. That's why it is semi-decidable but not fully decidable. That means it is undecidable. Okay. Now we'll see membership problem. So membership problem is actually undecidable. That means there is no total Turing machine for that. Okay. So what is membership problem? We'll see clearly. Membership problem is a language of strings in the form of m hash x where this Turing machine m halts on x. Example, let's say in your house there is a Turing machine called 0010 and it is, let's say, accepting input 01. Then 0010 hash 01 is one of the string in your membership problem. That's it. Similarly, there may be infinite strings. Maybe there are infinite Turing machines and based on their acceptance we are going to form this kind of strings m hash x. Okay, that's why simply in one line we say that membership problem is a language or collection of strings in the form of m hash x where m accepts x. Okay, for that there is no total Turing machine. Sir, but you have drawn it, right? Yes, I have drawn and I am going to prove that this kind of Turing machine doesn't exist. What kind of Turing machine? The total Turing machine for m hash x. That means for this kind of patterns. Really, for this kind of patterns, if there is a total Turing machine, then it should have only two states. That means it should always accept m hash x kind of strings and it should reject the strings which are not in the form of m hash x. Especially, what is the condition? M accepts x, correct? That means, example, you have a string 0010 which is a Turing machine and let's say 010 is input. Assume that, let's say, this Turing machine m does not accept 010. Then this total Turing machine should say should go to reject state. Now there is a Turing machine 0011 that accepts epsilon string. Then this input is given to this Turing machine. it should accept it, because this Turing machine is accepting epsilon, right? See, M accepts X, M and X. Here M accepts epsilon, then M hash X, this string is, a member of this membership language. So you have designed this Turing machine for membership problem, right? So it should accept it. That's it. Okay. Finally, your total Turing machine is going to accept sometimes, reject sometimes. If this total Turing machine is designed for this language, all the strings in this language will be accepted. For that, M should be, the condition is, see, this pattern belongs to this language only if M accepts X. That's why finally end of the day, simply I can say that. So this total Turing machine is a total Turing machine of this language. Then any Turing machine M accepts X, then your total Turing machine is going to dash state, accept state. Remember it. If there is a Turing machine M that rejects X, that means it is not accepting X. Otherwise, there is a Turing machine M loops on X infinitely, that means it is not accepting. These are the two cases generally a Turing machine won't accept an input. In that case, M hash X is not part of this membership problem, then your Turing machine for that membership problem should reject it. Then only it is a right Turing machine for that language. We know that, right? So finally, in these two cases, your total Turing machine is going to do what? Reject. Sir, when my total Turing machine will go to loop? You have forgotten complete story. Your total Turing machine will never loop, right? Because there is no loop thing. That is what total Turing machine. Total Turing machine never loops. Understand? So finally, this is a summary of membership problem. So membership problem has a total Turing machine. Then this will happen. You remember it. What it will do? So in simple English words, I can say like this: your total Turing machine is going to decide whether M accepts X or not. You see, very simple. We'll give M hash X to your total Turing machine. We'll ask, my dear total Turing machine, will you go to accept state or reject state? Example, let's say your total Turing machine goes to accept state. We know that this is the case. That Turing machine M accepts X. Now, if it goes to reject state, then definitely we can say what? Reject state. Then we can say maybe M is rejecting X through, going reject state, otherwise maybe looping. Correct? In that way, M loops on X or M rejects X, we can say by this reject state. That's it. So this is about your total Turing machine, but such total Turing machine cannot exist. I'm going to prove it. Remember it at this moment that let's say there is such total Turing machine. Assumption. I take a random Turing machine M. Don't ask me why, because using that I'm going to prove that this kind of Turing machine does not exist, total Turing machine. Okay, we'll see that. First of all, let me take a Turing machine. It is just Turing machine. Just Turing machine means in generally it may have three states. One is accept state, correct? So your Turing machine on input X eventually may go to accept state. We know that, right? Recall. So what is general Turing machine definition? It will have, final state, reject state, right? Eventually your Turing machine may come to final state or reject state, or sometimes, it may be in infinite loop, correct? So let me show them that possibilities are it will go to accept state or reject state or loop. Such Turing machine is M. Okay. Now to closely watch this one, I give input X. What this M will do? Do you know anything? No. It depends on its functionality. Maybe it will come to accept state and after that it will be staying there. Otherwise it will come to reject state and it will stay there. Otherwise it may be in loop. Correct. Now let me create another Turing machine which is, let's say, N. So this is very important Turing machine. Try to understand the functionality of that Turing machine. So N is a copycat. You know copycats, right? Copycats generally copy from others. So this Turing machine N is going to copy from M. Okay, that means Turing machine N is going to have a code of M. First of all, assume that let's say your Turing machine N is having exactly code as M. What is the behavior of M? What is the behavior of N? It will be equal to M, correct? Now assume that initially you have blindly copied total code from M. That means Turing machine N's code is nothing but Turing machine M's code. So transition functions are same, input alphabet, everything is same. Then what is going to happen? You see, if you give input X, what happens? Exactly same thing. If this machine accepts X, this machine also accepts it, correct? Remember it. If this machine rejects it, that means on that input X, if this machine M goes to reject state, this is also going to reject state. No doubt on that, because both are same. Example, let's say your friend has a C program, you copied it blindly, same program, and you modified the variables and all, then what will be the output? Same thing, right? In the same way here also, this machine is also going to do the same. Correct, but I am going to do little bit modification, because you know that things as a student, you copy from your friend's code and you do some manipulations, and somehow you prove that your code is different from your friend's code, right? That is the way you manage the things. Similarly here n is also going to manage like that. Okay, so it will take the code of M, closely observe what n is doing. In M, example, in M there is a state called T, right? Then, and first of all see local code. So this is M's code. In M there is a state called T, there is a state called R. Okay, now N is going to have a modification, that is nothing but this T and R both are modified to T. There is no reject state in N. Try to understand. So finally what I want to say is, your code of M is copied, right? On that T is modified to T, that means T is T remains same T, R becomes T. That means final state of M is final state of N, reject state of M is final state of N. Okay, so if really that happens, everything is same, then what happens to functionality, we'll see. I'll ask some questions, you tell me. Really on input X, if M accepts it, okay, M accepts it, that means that M is going to dash state on X, T state. Since you modified this T, because here also we have same code like M, right? But the only little bit extra. What is that extra? Whenever M goes to T state, we are also going to T state, because M's T is nothing but N's T, both are same. Okay, fine. If M go to reject state here, example if M goes to reject state, then what are you going to do? I write like this: M goes to reject state, R. Then what is going to happen here? Because here also M code, we are executing M's code only, exactly M's code, so that M also here also will go to reject state, but we modified R to T. Then here N Turing machine, in this N's Turing machine, we are going to dash state T state, that means accept state. Finally, can I say one thing? Whenever M accepts X or rejects X, we are going to dash accept it. Remember it. Okay, now can I say like this? The relation between M and N is like this: if M accepts X, then definitely here this N accepts X. Remember it. Correct? N accepts X. If M rejects X, then here also N accepts X. Here rejecting means going to reject state. Okay, that is what my intention. Finally, whenever M goes to T state or R state, that means it is nothing but halting. Whenever your M halts, I am clearly telling here what is the meaning of halting. If there is a Turing machine, if the Turing machine eventually go to T state or R state, that means final state or reject state, then we say that the Turing machine is going to halt. There is other cases going infinite loop, right? So now whenever your M accepts, M goes to final state, that means accept, or whenever your M goes to reject state R, then here N is going to accept state only. Such a way we designed it. Okay, now can I say one thing clearly? Finally, if M halts on X, that means M is going to T state or R state, then only we say it's halting on X. Then definitely here N is dash, N is accepting S, right? N accept X. That is the way we designed N. Okay, now sir, if M does not halt on X, think about it. That means if M does not halt on X, then M never comes to T state, R state. If M never comes to T state or R state, then this N is not going to come to T state. Correct or not? Because we link like this. Recall functionality of N. Functionality of N is simply like M, but in M, T state, R state are finally made T state. So if m never comes to t state or r state, that means m is in loop, then v never comes to t state, that means we never accept it, correct? So that's why I can say that m halts on x, then n accepts x. M does not halt on x, write it. If m does not halt on x, what is going to happen, you tell me? That means when you are in loop, then we never come to t state or r state. If you come to t state or r state, that is not a loop, correct? After that, if you loop also, we say that we accepted it, correct? So this is done already. So that means if m is in infinite loop without coming to t and r, then your overall Turing machine n cannot come to t state, correct? Then n will be in other state, right? So I can say that, if assume that, let's say m is in infinite loop, if m is in infinite loop, never it comes to t or r state, then never we come to t state of n, then n is going to reject it, correct or not? So n rejects x. So by these two observations, these two are very important. M halts on x, n accepts x. M does not halt on x, n rejects x. Go to propositional logic. Whoever have not attended my propositional logic, please attend it first. Logic is very important. Whenever I write P implies Q, this is P implies Q. If something, then something. If something, then something. If P, then Q. If Q, then P. See, this both are same. This is P, this is Q. If P, then Q. This is if Q, then P. Whenever both are correct, P implies Q, Q implies P, then we say that P is equivalent to Q. That means P if and only if Q. We write P if and only if Q. Remember it. If you know that if P, then Q, and you know that if Q, then P, okay, like this. P implies Q, Q implies P, then we write P double implies Q, okay? Similarly here I am removing this entire thing, okay? Finally I am writing double implication. How to write it? P. P means m halts on x. It's a two directional. Whenever m halts on x, if and only if n accepts x, that is decided, correct? Now if and only if is very easy to understand, don't worry. So don't think that sir has written a complicated thing. Very simple. If m halts on x, if this is true, then what happens? Your Turing machine m comes to t state or r state, then our n is going to come to accept state. Such a way we designed, yes or no? That's why m halts on x, n accepts x. If m does not halt on x, let's take it as false. If m does not halt on x, then m is an infinite loop, then we never come to t state, then definitely in that infinite loop we are going to reject it, correct? So finally m halts, n accepts. M does not halt, n reject. That kind of statements usually we write like this. M halts on x if and only if n accepts x. This is one important thing you remember. So finally we are going to now our original thing, recall. So this is very important point. Using this I am going to disprove this one. What was our initial agreement? That we assumed that for this kind of membership problem there is a total Turing machine. Okay, let's come to that total Turing machine again. Now we are going to make impossible thing is possible. Ran is going to do that. What is that impossible thing? We have learned halting problem is undecidable. That means for halting problem total Turing machine does not exist. That means if we cannot always say whether a Turing machine, random Turing machine m halts on x. In simple words, with respect to language problem, that is equal to saying that whether given m hash x, where m is a Turing machine code, x is an input, whether m Turing machine code is run on input x, whether it halts or not is undecidable. For that we don't have a machine which always say yes or no. Accept means yes, let's say reject means no. Then there is no yes or no machine, correct? We know that already. Now but we can construct yes or no machine by taking help of Raju. So Raju is claiming like this: I have a total Turing machine for m accepts x. That means my Turing machine will tell whether a random Turing machine accepts a random input or not. Oh, how? We'll ask. My dear Raju, can you say anything? Anything about any Turing machine? Yes, I can tell anything. Example, you want to know about a Turing machine called let's say y. Then you simply and tell me what input you want to know, x. Then give a string like this, y hash x. Then I will run. If you give y hash x, then I will tell about y. How you see? Simply run y hash x on me. Y hash x. Then I assume y as a Turing machine code and x as input, and I simulate this Turing machine code on x. If really the Turing machine accepts x, then I will go to accept state. If the Turing machine does not accept x, then I will go to reject state. Don't worry, don't ask me the functionality. It is confidential, secret. But when you give y hash x, I always tell whether y accepts x or not, for sure. Okay, now really it is correct. Rani also can build halting Turing machine, Turing machine for halting problem. How we'll see. But it is impossible. If you are proving that impossible possible through some assumption, because this is assumption. Raju's machine is assumption because he is not giving us functionality. That means he is just cheating us, correct? So we prove that Raju's machine cannot exist. Now example, let's say Rani wants to do impossible thing. What is that? Constructing a total Turing machine for halting problem. For that, how she is going to do, you see, anyone gives input m hash x to her Turing machine, what she is going to do is she is going to construct another machine n, and we know the relation between m and x, right? What is the relationship between m and n in the previous example? M halts on x if and only if n accepts x, correct? So that is the relationship. But we have a machine for n accepts x, correct? I use that machine. Let me go to that machine. Raju, you are a specialist in membership problem. I give you input n hash x. Tell me about n. Then definitely this machine is going to accept state or reject state. It goes to accept state. Definitely we can understand that n accepts x, correct? Otherwise we can say that n rejects x. We can easily find it out. Why? That is what Raju is claiming, correct? Now we'll take the result. So run this n hash x, then assume that let's say n says n accepts x. N accepts x, then definitely m halts on x. Then we can decide about m. So m halts on x. Okay. If n rejects x here, then we say m does not halt on x. In that way we can decide about m and x. Sir, you are only deciding about a particular Turing machine. Are you answering every Turing machine? Yes. If you have a Turing machine, give me. Example, your Turing machine is y. Okay. That Turing machine, you want to know whether it halts on input x or not, y hash x. Correct? For that, Rani can construct a total Turing machine. How? Simple. Rani is going to construct a new machine z. Did you remember? For m, how we constructed n? In the same way, by making Turing machine y's final state and reject state to final state, we can construct a new Turing machine z. That is, through finite control, through our machine code. So what we are going to do is, this is your problem, right? So instead of running this problem, we run this problem on this machine. We use this machine as a subroutine in our Turing machine. Don't worry. We take this Turing machine also into our code. Then we run z hash x here. My dear Raju, tell me about z hash x. Then Raju says that z hash x, if I give, my machine is rejecting. Oh, that means z does not, z rejects x. If z rejects x, we know the relationship between these two. Z rejects x because y and z are almost same, right? Then y does not halt on x. Such a way we designed, you see. M and n are two machines like y and z. If m halts on x, if and only if n accepts x. Here also, we know the relationship between y and z. Y halts on x if and only if z accepts x. Since here Raju said z does not accept x, then here also we can decide about y. What is y? Which is a Turing machine which is given by someone randomly. That means now Rani can answer about any Turing machine whether that halts on any input or not. But it is impossible. Such Turing machine should not exist. But she is using this Turing machine and she is answering answers, right? That means she is constructing this total Turing machine. So where is the mistake? So since it is impossible, this should be impossible, right? Through this, if it is possible, which is impossible, then that possible thing should be impossible. That's why. So Raju's machine definitely should not exist. If this exists, this exists. But this does not exist. Already we know that. Then this does not exist in that way. So Raju is lying. He is a liar. So he cannot have that kind of machine. Finally, we proved that. So there is no total Turing machine for this problem also. What is that? M accepts x. From now onwards, if you don't understand anything, like if you clearly don't understand anything, don't worry. Remember these two problems. One is whether m halts on x. Second one, M accepts X. Membership problem and halting problem are two languages. For them there is no total Turing machine. That's why the two problems are undecidable. If you remember it, then further we can proceed. Okay.